Welcome back to the second part of the lecture on ECC. Last time, I promised you to explain the strange condition on A and B in the definition of an elliptic curve. Here you can see that that expression is actually minus the discriminant of the polynomial x cubed plus ax plus b. You can also compute the discriminant as the square of the product of all pairwise differences of the roots of the polynomial. In fact, you can define the discriminant in a similar way for a polynomial of any degree. You have already seen this at high school in the context of quadratic polynomials. Recall that in that case, the sign of the discriminant influenced the number of real roots of that quadratic polynomial. Here we have something similar. Over the real numbers, the sign of the discriminant determines the number of components of the associated elliptic curve. Either it's just a single component or there are two of them. The edge case is when the discriminant equals 0. You can see from the definition that this corresponds to the polynomial having a multiple root. And this is exactly the reason for the naming. We want to discriminate the case of the polynomial having multiple roots. Because in that case, we get a singular curve, which has a technical meaning in geometric terms. So that's the reason why the definition of an elliptic curve requires a non-zero discriminant. You can see this works over any field, although over the finite fields you have no such things as the sign. But in that case it also does not make sense to talk about components as the curve is discrete. Alright, but what's so bad about the singular curves that we are so desperate to avoid them? Well, the problem is that they contain points at which we cannot define the tangents. And as we saw, having tangents is a crucial requirement for being able to define the group law. There are different flavors of singularity. On the left, we can see a singular curve whose singular point at the origin is called a cusp. The tangent at this point would be the x-line, but with a double multiplicity, which would be problematic. On the right, we can see a curve whose point at the origin is a singular point called a node. You could define two distinct tangents at this point, so it is not clear which one should we choose. In both cases, we can try to solve the problem by removing the singular points and defining the group law only on the rest of the curve. The good news is that in both cases, we really do get a group by doing that. But the bad news is that the groups that we get are nothing new. It's a fun exercise to show that in the first case of a cuspidal curve, the resulting group is isomorphic to the additive group of the field. With the nodal curve, you get a group isomorphic to the multiplicative group of the field, although I'm cheating a little bit there because there are some technicalities. Anyway, from the cryptographic perspective, we already saw that the DLP in the additive group is easy. In the multiplicative case, well, this is the classical finite field crypto, for which we already know sub-exponential attacks. That's basically why we can view ECC as a direct generalization of these cryptosystems. We sometimes talk about additive and multiplicative reduction. In any case, singular curves are just not good for cryptography. Now we can get back to actual elliptic curves. Whenever you define a group law on some object, it's only natural to ask, what are the possible group structures? And this theorem gives us an answer for elliptic curves over finite fields. The group is either cyclic or bicyclic, generated by either 1 or 2 points. In the notation here, the cyclic case occurs exactly when m1 equals to 1. This is a quite strong result, and at a very high level, you can view it as a consequence of the structure over the complex numbers. The torus is a product of two circles, and this property is kind of inherited, but the actual proof would take some work. Let's have a small example now. Consider the elliptic curve with the a coefficient equal to 1 and the b coefficient equal to 3. To find all the curve points over f5, we can simply try all the x and y coordinates, although soon we will see that there is a better way. In this case, we get 3 affine points, 1, 0, 4, 1, and 4, 4. And of course, there's also the point at infinity, O. This means that we have a group of order 4. There are two possibilities for the group structure. It can be either Z2 plus Z2 or Z4. The theorem above does not allow us to distinguish between these two cases, so we will need some further inspection. We already know that a point has order 2 if and only if its y-coordinate is 0. So for example, the point 1, 0 has order 2. But if the group was isomorphic to Z2 plus Z2, all of the points would have to have order 2, because multiplication by 2 annihilates both summands in that case. But clearly this is not the case, because the points 4, 1 and 4, 4 do not have order 2. So they must in fact have order 4, and the whole group is cyclic. You can notice that in this example, the number of points, 4, is quite close to the prime defining the field, 5. Sure, this is a very small example, but it turns out that this is only a very special case of a quite general phenomenon. It is summarized as the following theorem by Hasse and Wei. It says that the number of points of an elliptic curve over Fp is p plus 1 plus or minus some error term, and the error term is bounded by 2 square roots of p. So, for example, in cryptography, if you have a field Fp has a certain bit length, such as 256 bits, you can be almost sure that the group order of any elliptic curve over Fp will also have the same bit length. In fact, the upper half of the representation of both numbers will be the same. The theorem is interesting because you can view it as an instance of the Riemann hypothesis in the context of elliptic curves. Only, unlike the Riemann hypothesis, the proof of this theorem is not actually that hard. So, no $1 million awards for this, sorry. Anyway, it turns out that this bound is very tight. In fact, all integer values in this interval can be realized as the order of some group of an elliptic curve. To see this, you could use the complex multiplication method, which allows you to construct an elliptic curve with any prescribed number of points. But the method is quite advanced, and when you use it in practice, you can only get curves with a special property. But still, it's very useful to have such a classification. The distribution of the group orders in this interval also has a nice property. We will discuss this next. Let's say we want to compute all points on a curve over Fp. Instead of iterating over all possibilities for x and y, we can try all x values and see whether the evaluated polynomial fx is a square in Fp. It might be useful to recall that the multiplicative group of Fp is cyclic. This means that there is some generator G such that any non-zero element of Fp can be represented as a power of G. When you limit the exponent to the set 1, 2, up to p minus 1, this representation becomes unique. Then we can say that a non-zero element of Fp is a square in Fp if and only if the exponent of this representation is even. It follows that exactly 1/2 of all non-zero elements of Fp are squares in Fp. Moreover, the product of two squares or a product of two non-squares is again a square, whereas the product of a square and a non-square is a non-square. Now we can try to count the number of solutions to y squared equals fx. If f evaluates to 0, then y squared must be a 0, so y must be a 0 as well. So we have a single solution. If f evaluates to a square in Fp, then there are exactly two solutions for y, which differ by a sign. And finally, if f evaluates to a non-square, then the equation has no solutions for y and we get no points. Now, let's do a little trick. Instead of counting only the points of E, let's also count the points of ED, which is another curve given by the same cubic polynomial, only instead of y squared, we have d times y squared, where d is a fixed non-square in Fp. Such an elliptic curve is called the quadratic twist of E. Actually, you might object that such a curve is not an elliptic curve according to our definition, but this is only a minor technical issue that can be fixed easily. So let us now count points on the quadratic twist as well. You can see that the first case, when f evaluates to 0, remains exactly the same, but the numbers of solutions for the next two cases have now exchanged. This is because d is a non-square, so that d times y squared is also a non-square. Let's sum up the number of solutions in each row now. In the first case, we get 1 plus 1, in the second 2 plus 0, and in the third 0 plus 2. So yes, that's correct. For any x we try, we get 2 solutions in total. Since there are p choices for x, that gives us 2p solutions in total. But remember, these are only the affine points. So for both of the curves, we must also count the point at infinity. We have just shown that for any elliptic curve E, the number of points on E over Fp plus the number of points on the quadratic twist of E is always 2p plus 2. We can formulate this differently by saying that if E has p plus 1 plus t points, then the quadratic twist of E has p plus 1 minus t points. Notice that t is exactly the error term that we talked about in the Hasse-Weil theorem. So we have just shown that the distribution of possible group orders in the Hasse-Weil interval is symmetric with respect to its middle point p plus 1. You can also prove stronger claims about the distribution, but that's beyond the scope of this lecture. You can probably guess that when p is large, iterating over fp probably won't be the best idea. Luckily, there is a polynomial time algorithm by Schoof that counts the group order. It's very practical and very useful. For example, we can now assess the security of the DLP for any given curve, because the security mostly relies on the group order. We already know that when the group order is highly composite, we can use the Pauling-Hellman attack that breaks the DLP into several smaller and easier instances. To avoid this, we are aiming either for a curve with a prime number of points, or possibly a prime number times a small cofactor. This is mainly because in some cases the cofactor cannot be avoided completely. Then we can select any generator of order q and publish it along with the curve, so that it can be used as a basis for the DLP. Namely, if the curve and the generator g are both public, and someone generates a private key k and computes the multiplication k times g, recovering k is the hard problem on which we can build cryptographic protocols. This is the case for both ECDH for key exchange and ECDSA for digital signatures. As far as we know, the choice of the generator G does not really affect security and doesn't matter that much at all. But you can ask, what does affect security? We already know that there is the Pauling-Hellman attack, the polar throw attack, and the baby step giant step attack, but are there any attacks that are specific to ECC? It turns out that the answer is yes. Elliptic curves that have p points over fp, which are called anomalous, are vulnerable to the SASS attack. It reduces the DLP instance in an elliptic curve group into a DLP instance in the additive group of the finite field. And we already know that the DLP is easy in that group. This attack is also called an additive transfer. And just like with the singular curves, you can probably guess that there is also a multiplicative transfer. It applies, for example, to supersingular curves, which are curves that have p plus 1 points over fp. Do not get confused. The word supersingular has absolutely nothing to do with singular curves that we saw earlier. It's just unfortunate terminology. Supersingular curves are a special case of curves with a low embedding degree, which is the multiplicative order of the prime p modulo the largest prime factor of the group order. When the embedding degree is low, the curve is vulnerable to the MOV attack that uses pairing for the DLP instance reduction. Pairings are special maps that take two elliptic curve points as an input and output some root of unity. They are also used constructively in pairing-based crypto, which allows nice features, for example in the Zcash cryptocurrency. By the way, supersingular curves can also be used constructively in isogeny-based crypto. More on that later. And that's it. If you are expecting more sub-exponential attacks on the ECDLP, I have to disappoint you. It really seems that the ECDLP is secure, at least in theory. Both attacks described on this slide only depend on the group order, and they are very rare in the sense that almost certainly you will never encounter an elliptic curve in the wild that is vulnerable to one of these attacks. So in practice, these attacks are really not that relevant. And this absence of a sub-exponential ECDLP attack is exactly the reason why we can use relatively small elliptic curves that still offer a very high level of security, at least theoretically. This is a very big advantage compared to RSA and finite field crypto, because in both of these you have sub-exponential index calculus attacks, so you must use much bigger parameters to get the same level of security. But of course, we can only talk about the security of these crypto systems based on the publicly known attacks. So there is always the possibility that we do not know the whole story yet. In any case, before you get too optimistic about ECC, let me just remind you that ECDLP security does not always translate to ECC security. The real world is dark and full of terrors, so even when the math is secure, you still have many different ways of attacking practical implementations. We will explore that in the next video, so stay tuned.